Okay, what's the difference between an even function and an odd function? An even function is a function that's symmetric with respect to the y-axis. So the y-axis is an axis of symmetry. Everything over here is reflected over here, and everything over here is a reflection of everything over here, and vice versa all the way through. Okay, so the condition is that what you have on this side of the y-axis is identical to what you have at the same distance on this side of the y-axis. That means that f of negative x has to be equal to f of x. So there's our condition for an even function, and that's our test. We have to use this test if we are asked to find whether a function, to test whether a function is even or odd. It's not sufficient to sketch a graph and say, yeah, it is. You have to use the test to get full credit, at least. An odd function is just the opposite. F of negative x would equal negative f of x. That way, what you have up here gets flipped over, and that's what you have down here. As, for example, for an x cubed function, and we'll show that in a minute. Okay, so we do the tests for two of our basic functions, the x squared and x cubed functions. Okay, for the x squared functions, f of negative x is, well, we replace x with negative x, and we get negative x quantity squared, and of course negative x quantity squared is equal to x squared. Thus, f of negative x, which is equal to x squared, is equal to f of x, which is also equal to x squared. Then I could enhance this a little bit by saying that both of these are equal to x squared. This is an even function then, meaning it's symmetric with respect to the y-axis. And that's obvious from the table and the graph. The table tells us, well, negative 2 and 2 give us the same result. There's where an example where f of negative x, if x is 2, f of negative x would be f of negative 2, but it has the same value as f of 2. And the graph is clearly symmetric with respect to the x-axis. And since we're intimately familiar with this table and this graph, we should fully understand that symmetry and how this test validates the symmetry. Now we have f of x equal x cubed, and I don't even know where I've written down that we're doing the cubing function here. But I did, you know, it was clear in class. Okay, so let me just say if f of x equals x cubed, then I've set it up here, that big line there. Okay, let's start up here. Sorry. F of x is, if f of x is x cubed, then what is f of negative x? F of negative x equals what? This is always the first step in determining whether a function is even or odd, because both tests involve evaluating f of negative x, don't they? And then comparing with f of x. Is it equal to f of x? Is it equal to negative f of x? Okay, so f of negative x is the cube of negative x. We just plug negative x in for x here and here, and we get this. And that's, of course, if we cube negative x, we get negative x cubed. Now, is that equal to f of negative x? If so, it's symmetric with respect to the y-axis. Or is this equal to negative f of negative x? If so, then we're symmetric with respect to the origin. And I'll remind you what that is with this picture here. Okay, well, let's see. Test f of x equals negative x. That would say that x cubed equals, well, f of negative x is negative x cubed. Well, x cubed is equal to f of x, negative x cubed is equal to f of negative x. They're not equal, so I say it ain't so. So we don't have symmetry with respect to the y-axis. It's not an even function. Okay, what about f of x equals negative f of negative x? That says that, well, f of x is x cubed, f of negative x is negative x cubed, And negative f of negative x will be the negative of negative x cubed. And that is so, this x cubed is equal to the negative of x cubed, since the negative of x cubed is x cubed. So this is symmetric with respect to the origin. It's also an odd function, and I didn't emphasize the even function. But this is an even function because of this. And this is an odd function because of all this. An odd function is symmetric with respect to the origin. We'll see what that means, as I said. Looks like I've got an 81 there. This thing here is part of my brace. So it doesn't look like a great brace, but I think you see. Okay, well here are the values we get for the x cubed table. Here's x, here's y equals x cubed, and we're very familiar with these values, and we're very familiar with the way the graph looks. Now, if x is a value out here, then negative x lies at an equal distance on the other side of the y-axis. The value on this function corresponding to x, whatever x is the y-coordinate here, and the value at negative x is the y-coordinate down here. The condition that we satisfied here says that this is the negative of this. And that's pretty clear, equal distance down here to up here, because the function has the symmetry it does with respect to the origin. And that means that if I connect this point here, well, if I pick any point on this graph, if it's accurately drawn and make a line segment to the origin, then continue that line segment at an equal distance beyond the origin, I'll strike the graph down here. Okay, so this value is equal and opposite to this value because this triangle is similar to this triangle. And those are ideas that would be worth thinking through and understanding. Now, one example I didn't do would be a function that's neither. And one of your basic functions, I have to do this in small space, but f of x equals 2 to the x. Now I'm just going to show you that f of negative x then is 2 to the negative x, which ought to be very clear. And 2 to the x is not equal to 2 to the negative x, unless x happens to be 0. And I'm not going to, well, okay, unless x equals 0. Because what? 2 to the negative x is the reciprocal of 2 to the x. Well, the only number that's equal to its reciprocal is 1, and that's what you get if x equals 0, okay? And then 2 to the x is clearly not equal to negative 2 to the negative x, because this is always positive and this is always negative. That would be a little hard to read my words here. I've just said that this is always positive, this is always negative. So it can't be equal. So here's an example of a function that's neither even nor odd. It's neither symmetric with respect to the positive x-axis or with respect to the origin. And of course, you can look at the graph of 2 to the x and see that it has this shape. It's clearly different on this side of the origin than it is on this side of the origin. And there's no way you can reflect a point of this graph through the origin, because this graph, and get a point on the graph, because every value of 2 to the x is positive. It can't be negative. And if you reflect a point points on the positive side of the x-axis through the gorge, and you get a point on the negative side. And you can draw it and see that you couldn't possibly do this, and that the reflection is clearly not equal to the function itself.